Okay, so this week we deal with continuous probability. Continuous random variables. Remember, random variables may be classified as discrete or continuous. Discrete random variables are a random variable that assumes a countable number of distinct values. The continuous random variable, which we discuss this week, is the random variable is characterized by infinitely uncountable values within any interval. Okay, so first we're going to look at the continuous uniform probability distribution. So when computing probabilities for continuous random variable, keep in mind that P, the probability of capital X equals little x, is equal to 0, where capital X is the continuous random variable and little x is a particular value such as 7. We cannot assign a non-zero probability to each infinitely uncountable value and still have the probability sum to 1. Thus, we have to calculate the probabilities that the random variable falls within some interval. Now, since the probability of x equals a and the probability of x equals b are both equal to 0, then the following holds for continuous random variables. We can say the probability that x is between a and b with the inequalities less than or equal to, or with just strictly less than, or 1 less than or equal to and 1 less than, and the last two cases are all the same. Now, the probability density function f of x, little f of x note, of a continuous random variable x describes the relative likelihood that x assumes a value within a given interval. For example, probability that x is greater than or equal to a but less than or equal to b, where f of x is greater than 0 for all possible values of x, and the area under f of x over all values of x equals 1. Now we have a cumulative density function, capital F of x, of a continuous random variable x. And for any value, little x, of the random variable capital X, the cumulative distribution function f of x is computed as f of x equals the probability x less than or equal to x. And so therefore, what we can do is we say the probability that x is greater than or equal to a, less than or equal to b, is equal to f of b minus f of a. So we're just taking the upper minus the lower. We're just converting this into the f of whatever, and we're using the b minus the a. Now for the continuous uniform distribution, it describes a random variable that has equally likely chance of assuming a value within a specified range. The probability density function is f of x equals 1 over b minus a for all x greater than or equal to a but less than or equal to b, and equals 0 for x less than a or x greater than b. So a and b are the lower and upper limits respectively. Now, the continuous uniform distribution, we can find an expected value and a standard deviation of these as well. The expected value is just mu, and that's a plus b divided by 2. And the standard deviation is equal to sigma is equal to the square root of the quantity b minus a squared divided by 12. Or if we wanted to, we could find the variance first, and that's just the b minus a quantity squared divided by 12. And then take the square root of it to get the standard deviation. All right, so the graph of a continuous uniform distribution looks like this. The values a and b on the horizontal axis represent the lower and the upper limits. And our height, 1 over b minus a, it doesn't represent a probability, that's just the height. So that's where the height is. And it's the area under f of x that corresponds to the probability. So the whole area under here is equal to 1. Here's our mean, a plus b divided by 2. And so we can find different areas. So for example, based on historical data, sales for a particular cosmetic line follow a continuous uniform distribution with a lower limit of 2,500 and an upper limit of 5,000. Now remember, we had we're going to find the mean and the standard deviation as a plus b over 2 and the square root of the b minus a quantity squared divided by 12. So what are the mean and standard deviation of this uniform distribution? Well, A is 2,500, that's lower number, and 5,000 is upper, so that's going to be B. So we just plug those into those values equations we just looked at. And so for the mu, we get 2,500 plus 5,000 divided by 2, or 3,750. And for the sigma, we get the square root of the quantity 5,000 minus 2,500 squared divided by 12, which is 721.69. Now, what is the probability that sales exceed 4,000? So probability x is greater than 4,000? Well, we're just going to do base times height, because we know the lower limit is 2,500, we know the upper limit is 5,000, we know the height, which is the 1 over b minus a. So we just need to take and figure out this length, which is 5,000 minus 4,000, or 1,000. The height is going to be the 1 over b minus a, so the 5,000 minus 2,500 is in the denominator. And if we do that, that's 1,000 times, and then this whole part reduces to 0.0004. Multiply those together, we get 0.4 as our probability of x greater than 4,000. What if we want to do it between two areas, say in the middle here? Well, we have a lower limit, we have an upper limit, and so all we have to do is find that difference to get basically our length. And so 3,800 minus 3,200, and we multiply that by that height we found already, which is the 0.0004, and so 600 times that is going to give us 0.24 for the area in the green. We also are going to look at the normal probability distribution, and the normal distribution, or the Gaussian distribution, is symmetric. It's bell-shaped, closely approximates the probability distribution of a wide range of random variables such as heights and weights of newborn babies, scores on SAT, and the cumulative debt of college graduates. And it serves as a cornerstone of statistical inference. Now, some characteristics of the normal distribution. It's symmetric about the mean. So here's our mean, symmetric about that. That means the mean equals the median is equal to the mode, which is right here. It's asymptotic, which means it gets really, really close to the x-axis, the curved part here. It gets really close, but it never actually touches that x-axis. Oh, and one other thing is, the probability of x greater than or equal to mu is equal to 1/2, and less than or equal to mu is equal to 1/2. So both sides are equal. All right, some characteristics. The normal distribution is completely described by two parameters, mu and sigma squared. Mu is the population mean, which describes the central location of the distribution, and sigma squared is the population variance, which describes the dispersion of the distribution. Now, the probability density function of the normal distribution. So for a random variable capital X with mean mu and variance sigma squared, we can find the following. And what we're going to do is we're going to end up using the square root of that to get just a plain sigma. So f of x is equal to, and now remember, this is for the normal distribution probability density function, 1 over sigma square root of 2 pi, and then exp means e to the some power, and the e to this whole thing here. So a minus x minus mu quantity squared divided by 2 sigma squared. And again, pi, that's 3.1415, so on. And if you use your calculator, it'll put what it can have in your calculator's memory. Expx, that's e to the x, like I said. And e is just about 2.718. But again, if you use your calculator to solve this, or even Excel, it'll plug in the actual values you need instead of rounding errors. So for example, suppose the ages of employees in industries A, B, and C are normally distributed. And these are the parameters, mu's and sigmas. So A, we have mu 42, sigma 5. B, we have mu 36, sigma 5. And C, mu 42, sigma 8. So if you notice in the first two, our sigma is the same, but our mu's are different. Then the last two, or the first and the last one, I should say, our mu's are the same, but our sigmas are different. So that's kind of what we're going to key in on there. And so let's compare these looking at the normal curves. So for A and B, like I said, the mu's were different. So basically, we're moving the curve left and right, depending on which one we start with. If we start with A, that's here at 42, and then we'll move to the left to get the mu of 36. And again, that's where the peak is at that point. Now, the sigmas was the same. So the sigma were both 5, I believe. And so because of that, the shapes of the curves are identical. Okay, so sigma being the same, shapes are the same, just shifting the mu position on that x-axis. Now, if we looked at the A and C, here we had the same mu, which was 42, but our sigmas are different. And so what it's basically showing us, the higher the mu, the shorter and fatter it is, because it's going to be more variables, so it's going to be wider. And when you make something wider, it also has to get shorter. And so the higher the sigma, the shorter it is, and the wider, the narrower the sigma, the smaller. It's going to be a narrower peak, and it's going to be taller. All right, so we're going to look at the standard normal z distribution. So a special case of the normal distribution where the mean mu is equal to 0 and the standard deviation sigma is equal to 1. Okay, so here, this is the standard normal. And again, mu is equal to 0 and we have a standard deviation of 1. And again, we have the probabilities of each side being 1/2, but instead of just z greater than or equal to z, it's going to be of 0 because we already know what that 0 is. So standard normal table, the z table, it's in our book, gives the cumulative probabilities, probability of capital Z less than or equal to z for positive and negative values of z. Now, since the random variable capital Z is symmetric about its mean of 0, probability of capital Z less than or equal to 0 is the same as probability of capital Z greater than or equal to 0, and that's that 0.5, and that's what we saw in that previous picture. And to obtain the probability of capital Z less than or equal to Z, we're going to look at our table. First, we're going to read down the Z column initially, and then across the top to get the more decimal points. So what we would do is we would go down here until we got to whatever our first part of the thing was. So say it was 0.34. So we'd go down here to 0.3, then we have to go across to the 0.04, and so that would give us 0.34, so 0.6331, excuse me, would be our probability. And similarly, for the negative values, you go down to whatever the negative value was here, maybe negative 3.7, and maybe it's 2, and so negative 3.72 is 0.0001. Okay, and so that's how we're going to do it. Here's an example. So let's say we want to find the probability for a given z value. We're going to transform the normally distributed random variable into the standard normal random variable and use the z-table to compute the relevant probabilities. So the z-table provides the cumulative probabilities, remember, of z less than or equal to z for a given z. And so we want to find the probability of capital Z less than or equal to 1.52. So it kind of explains it here on the table. But this is really what table we're going to be using. We have the Z's coming down here, and we have the second decimal place going over here. So 1.52, so we come down here to 1.5, go over here to the 0.02, and 0.9357 is going to be our value for the probability here. And hopefully we get that 0.9357. And so that's going to be our probability. And usually what we do is we always draw a figure just because it's easy to say. So at 1.52, if this is 0 for the mean, 1.52 is to the right. And arbitrarily, it doesn't matter where you draw it. It's somewhere over here. So we know that probability up to that point right there, remember it's less than or equal to that value, is going to be 0.9357. Now what if we instead wanted greater than 1.52? Well, remember the area under the whole curve is 1. So if we want greater than 1.52, we take 1 minus the what's less than or equal to, and we get 0.0643 for that answer. Now let's say we want to find the probability for a given negative z value. So before we did positive z, now let's do the negative. Excuse me. Remember that z-table provides cumulative probabilities. In this case, probability z less than or equal to z, and we're going to have probably a negative z since we're looking at negatives. And so since z is negative, we can look at this probability from the left page usually of the z-tables, and that's what this one is. Okay, so we're going to go down here, and a better looking number, negative 1.96. So we go down here, negative 1.9, and we go over here to the 6, and we get 0.0250. And if we look over here, that's what the negative 1.96 is, 0.0250. And remember, zeros here, so negatives to the left, and it's somewhere out here. And again, arbitrarily, if you're just drawing it by hand, it doesn't have to be exact. And so that's right there. So if that's 0.0250, the whole thing's 1, that means the probability z greater than negative 1.96 is going to be the rest of the table. So 1 minus that is 0.9750, and that's what we get here. And these tables are kind of just to show you what we're doing with going down and over, but it's kind of saying, okay, well, you go down to the negative 1.9, then you go over to the 0.06, and then that's the value you get. But I think it's sometimes better just to see the full table. All right, so now what if we want to find probability between two numbers? So let's say we want the z greater than or equal to negative 1.52, but less than or equal to 1.96. So arbitrarily, again, I'm going to draw a table or a figure here. Negative 1.52 is going to be here on the left. 1.96 is here on the right, and this is so I can draw something and understand what is happening here. So remember, with our probabilities, if we look at the table, it's going to be z less than or equal to 1.96. So it's going to give us the probability from that point all the way to the end. Okay. Now, if we happen to look up negative 1.52, that's going to give us a probability from here all the way to the end. So basically, this one will give us a probability here, and this one will give us a probability all the way down. But we want the probability between the two. Well, what can we do? What we're going to do is we're going to take the larger minus the smaller, and we're going to be left with what's in the middle, which is the green. So we're going to look up 1.96 in our table. And if we go back, 1.96 is 0.9750. And that's what we have here. And negative 1.52, negative 1. So it's 0.0643. Take that probability, subtract off the other one, and we get 0.9107 for the probability of the green area. And again, we're taking the whole thing, then we're subtracting off just that part, and that gives us what's in green. And here's what I'm showing you, how I do it, and just arbitrarily drawing figures just to help me understand what the question is asking. So finding the following probabilities based on the standard normal variable, and we're going to use the tables on the next 2 pages. And we'll start off using them, but then after a while, you just have to accept it, otherwise it's going to take forever to get through all these. So we want to find the probability z less than or equal to 1.32. So I draw my graph. 1.32 is going to be somewhere over the right, and we want to find this yellow area. So 1.32, we go over here, and that's going to be 0.9066. And that's what our probability is. Now what if we want probability of z greater than 4.2? Well, we draw our thing, and 4.2 is way over here, and we want the probability that it's greater than right here. So what we need to do is we need to find probability that it's going to be less than or equal to, so basically everything over here, and we're going to subtract that from 1. Well, if we look up 4.2 in the table, guess what? It's not here. That's because anything greater than 4 is equal to 1, and so 4.2 is basically going to be a 1. So 1 minus 1 is 0, so the probability that it's greater than that 4.2 is 0. Now, between negative 1.28 and 0. Okay, well, again, I'm going to draw my picture, and here's 0. We know that. That's the mean. And we're going to have negative 1.28 over here somewhere. And we want to have the white area here, basically, between the two. Well, how do we do that? Well, first we're going to find the probability less than 0. Well, that's a half, because remember, the table split at the 0 mark, and half's on each side. But so that means we just have to find that probability of the negative 1.28. And so we go to our table, negative 1.281003. And so we take a half minus what's over here in the green, which is 1.1003, and we get 0.3997 for the value here. All right, so then we want to do one between 1.32 and 2.37, so they're both on the positive side. So we have 0 here. Here's going to be our 1.32 arbitrarily, 2.37, again, arbitrarily. And we're going to look for the purple area. And so what do we know? Well, if we find the area for the 2.37, that's everything. If we find the area for 1.32, that's kind of this teal color, and if we take the larger minus the smaller, we should get the purple. So looking in the table for 2.37, we get 0.9911. For 1.32, we get 0.9066, which we found up here, and that gives us 0.0845 for the area between 1.32 and 2.37. All right. We can also go the other way. So instead of finding the z value in the table and getting a probability, we can start with the probability and find the z value. So it says find the z value for a given probability. Well, it's 0.6808. I highlighted it because it sometimes takes me a while to find these, and so that is 0.47. And so we go to the table, find the 0.608, and it corresponds to that 0.47, which I said. And again, if we think about that, 0 is right here, 0.47 is just to the right of that, and so that area is already given as 0.6808, and it makes sense that it's greater than a half, and so I think we've done this right. Now we want to find a z for the given probabilities, and again, we're going to use the tables over here. So we want to find the probability z is less than or equal to z for 0.9744, so we know it's going to be this area over here, and so we need to find out what is that value. So 0.9744, that is this one, so that looks like 1.95, and that's what we get. Now here we want probability z greater than z, but remember we always want to find in the table it's always p less than or equal to z, so that means we're going to have to take 1 minus that value to get the value we're looking for. Okay, so what we're looking at is, it says that this value up here is 0.8389, okay, but we want what's less than over here. We need to find that in the table, so then we can look up what the z is for that value over here. So we have to take 1 minus this, which will give us what's in here, and that gives us, if we go to our table, 0.1611 is going to be a -99. So that means that z right here is going to be a negative 0.99. So again, that's 0. We go over here, 0.99, which is negative. Now we're going to have a z between negative z and positive z. So we have a negative z here, positive z here, and we know that the middle part here is going to be 0.95 between those two. So what does this say? Well, 0.95 is the middle, so that leaves an equal part here and an equal part here. Well, 0.05 divided by 2 is going to give us 0.025 here and 0.025 here. So if we add the total two together, that's going to give us 0.975. And if we look in a table for 0.975, that's going to be 1.96. And that's going to be what z is equal to. So it's going to be a positive 1.96 here, and it's going to be a negative 1.96 here. Now think about that. Negative 1.96, oops, wrong direction. Negative 1.96 is going to be 0.0250, which is what we said that area was going to be already. So we know we have the right answer again. Excuse me. All right, so now between 0 and z, so here's 0, here's z. Well, we know at 0, this is a half over here. And so we know that between 0 and z, which is right here, is 0.3315. So here what we have to do is we have to add those two together to get where we're at z. So 0.5 plus the 0.3315 gives us 0.8315. If we look that up in the table, we get 0.96. Okay. Now what if we have z and then 0, and so we have a z here, z is somewhere on the left, and we know it's going to be negative because if you're going to be between z and 0, it has to be on the negative side. And so we know at 0, that's equal to 0.5, but we know that between those two is 0.1772. So to get what is over here that's less than or equal to z, which will give us a z then, we have to take that whole thing, 0.5 minus the 0.1772, which gives us 0.3228. And once we find that value in the table, which is negative 0.46, that's what the area under here is, 0.3228 for the z of negative 0.46. And then one more. Probability of 0.4 less than or equal to z, less than or equal to little z. And so we know this time z is going to be over here somewhere. 0.4 is here. And we know that between them is this 0.3368. Well, what do we know about the 0.4? Well, we can look that up in the table. And when we do that, that's going to be 0.6554. And we're going to add that to what the red part is, 0.3368. And that gives us 0.9922 for what that z value is, or as far as the probability from there to the left. And so if we look that up, that's 2.42, and that's going to be what our z is. All right, so moving through the tables, here we have the standard normal distribution. So this is kind of revisiting our empirical rule. So with one standard deviation above and below the mean, we're going to have a probability of 0.6826. Probability is going to be 0.9544 between 2 standard deviations of the mean, and it's going to be 0.9973 between 3 standard deviations of the mean. Now this will help us do certain kinds of problems, such as the next one. So here it says average rent in a city is $1,500 per month with a standard deviation of 250. Assume rent follows a normal distribution. Use the empirical rule for normal distributions to answer the following questions. What percentage of rents are between $1,250 and $1,750? What percentage of rents are less than $1,250? And what percentage of rents are greater than $2,000? Okay, well first let's graph it. So we know the mean is 1,500, and if we take one standard deviation below, that's 1,250, one above is 1,750, and then we could do another one below, that would be 1,000, and another one above would be 2,000. So that's kind of where we're at with our graph. Now let's look at the problems. What percentage of rents are between 1,250 and 1,750? Well, that's one standard deviation above and below, and if we remember, that was 68.26% of the rents. That was the probability of 0.6826. So if they want a percent, we have to convert it to the 68.26%. Now, usually, most books always keep it as probabilities, but for some reason, the book I took it out of said they wanted it in percentage, so that's why I'm doing this, to kind of show you that some books do different things. All right, so now what about the percent less than 1,250? Okay, well, 1,250 is here, and so what do we know about that? Well, between here and here, we know that that's half of the 68.26, so that's 34.13, and we know that the whole half is 50%. So if we take the whole half, 50%, minus that 34.13%, which is here, that will give us what's left, which is 15.87% of rents are below 1,250. Now, if we are wanting greater than 2,000, so that's going to be one standard deviation, 2 standard deviations. So we want greater than 2 standard deviations above the mean. Okay, well, what do we know about that? We can do the 99.73, divide it by 2 and get that half of it, and then subtract that from 50, and we end up with such a small number. 2.28% of rents are greater than 2,000. So that's all that's left after you subtract off this part here, 1, 2 standard deviations, and actually it's dividing by 95.44, not 99.73. So the 95.44, and when you do that, then you get this value here. Have to read the right line. All right, so that's how that one works. Now we can use the normal distribution and solve problems too using our normal transformation. So we already know how to use the z-score, and this is what we would do for the z-score. Now we can say any normally distributed random variable capital X with mean mu and standard deviation sigma can be transformed into the standard normal random variable z capital as follows. And so basically we are following the same thing. And as we constructed this, remember the expected value or the mean is 0 and the standard deviation is 1. So a z-value specifies by how many standard deviations the corresponding x value falls above if z is greater than 0, or below when z is less than 0, the mean. A positive z indicates by how many standard deviations the corresponding x lies above. A 0z indicates the corresponding x equals mu. And a negative z indicates by how many standard deviations the corresponding x lies below the mean. Now we can also do the inverse transformation. We can start off with the z-score, and if we know the mu and the sigma, then we can solve for x. And so we can go from the z to the x, and all we're doing is we're just rearranging it, solving this equation for x, and then we can plug in our mu, our z, and our sigma and get our x value out. Okay, and so here, looking at this example, scores on a management aptitude exam are normally distributed with a mean of 72 and a standard deviation of 8. What is the probability that a randomly selected manager will score above 60? Well, first we have to convert this into a z-score. So again, it's just going to be the x, which is 60, that's what we're looking at, minus the mean of 72, divided by the standard deviation of 8. That's a negative 1.5. Okay. Now we want to know the score above 60. So If we know 1.5 is here, remember that's 0, and negative 1.5 is here, we want to have this value here. But in the table, if we look up negative 1.5, it's going to give us this white area over here. And so what we're going to have to do is we're going to have to take 1 minus this white area to get the yellow area. So if we do that, 1 minus the probability is z is less than or equal to 1, negative 1.5 is going to be 1 minus a 0.0668, or the value of the yellow area is 0.9332. Now let's go and use going backwards. Instead of going and finding the z value, let's find the x. So first introduced in LA, the concept of Korean-style tacos sold from a catering truck has been gaining popularity nationally. This taco is an interesting mix of corn tortillas with Korean-style beef garnished with onions, cilantro, and a hash of chili soy-dressed lettuce. Suppose one such taco truck operates in the Detroit area. The owners have estimated that the daily consumption of beef is normally distributed with a mean of 24 pounds. It's normally distributed, mean 24, and a standard deviation of 6. While purchasing too much beef results in wastage, purchasing too little can disappoint customers. So what we need to do is determine the amount of beef the owner should buy, the X value, such that it meets demand on 80% of the days. And how much would they have to buy if they wanted to meet demand on 95% of the days? So let's look at our equation again. So we know mu, that was our equal to 24. Standard deviation was 6. And our z is what was given. So for part A, it was 80%, so that's going to be the 0.8. And part B, or the number 2, they wanted 95%, or 0.95. So given that the P of Z is less than or equal to 0 is 0.8, we find this in the table. So you actually have to look at all the values in the table, and that gives us roughly 0.84 for a Z value. So we plug that into our equation. 24 plus that 0.84 times 6 gives us 29.04 pounds that they would have to buy to make sure 80% were happy. Now, if they wanted to make sure 95% were happy, you look that up in the table, and we get 1.64 for Z. Plug that into this equation, and we get 33.84 pounds they would have to buy to make 95% happy. So just that 15%, they just had to buy just a few more pounds to make it happy, and that's how it worked. All right, so exponential distribution. A random variable x follows exponential distribution of its probability density function is f of x equals lambda e to the minus lambda x for x greater than or equal to 0, and lambda here is our rate parameter. And the e, again, is just the exponential value. And for the exponential distribution, the expected value, or mu, is equal to the standard deviation is equal to 1 over lambda. Now, the cumulative distribution function, on the other hand, this is a probability of capital X less than or equal to little x is equal to 1 minus e to the minus lambda x. Okay, so that's for less than or equal to. What if we wanted greater than x? Well, we're going to take 1 minus this, and so probability x greater than x is 1 minus this value here, and when you take 1 minus that, you end up with just e to the negative lambda x, because the 1's cancel, and a minus is a plus. So these are what exponential distributions kind of look like. So basically, we're looking at parameters with lambda greater than 0. So here's 3 different examples of different lambdas. So let's do an example here. Assume a Poisson random variable has a mean of 6 successes over a 120-minute period. We want to find the mean of the random variable defined by the time between successes. All right, so if we have 6 out over 120 minutes, we have to divide the 120 minutes by 6 to figure out the time between 1. And if we do that, that's going to be our new exponential, and that's just 20. Basically, it's going to be 20 minutes between successes. Now, that's mu, so remember, our lambda is equal to 1 over mu, so what is the rate parameter of the appropriate exponential distribution? Well, lambda equals 1 over mu, or 1 over 20 in this case, and that's 0.05. Now, what if we want to find the probability the time to succeed will be more than 60 minutes? Remember, usually it's less than or equal to 60, and greater than is going to be just e to the minus lambda x. So e to the minus 0.05 times the 60, and that gives us 0.0498. Okay. All right, here we have a hospital administrator worries about the possible loss of electric power as a result of a power blackout. The hospital, of course, has a standby generator, but it too is subject to failure, having a mean time between failures of 500 hours. So it's saying only one failure is 500 hours. So that's we don't have to do any divisions to figure out any rates here or mu's. And it's reasonable to assume that the time between failures is exponentially distributed. What is the probability the standby generator fails during the next 24-hour blackout? So less than or equal to 24, basically. And suppose the hospital owns two standby generators that work independently of one another. What is the probability that both generators fail during the next 24-hour blackout? So basically, two would be this one and this one. Okay, so here, again, they said between the one failure was 500 hours, so mu is equal to 1 over 500, so that's going to be 0.002. And they wanted the probability x less than or equal to 24, the 24 hours. So we just plug that into our equation, 1 minus e to the minus 0.002, and then times the x, which was 24. Plug that in, we get 0.0469. Now, if we had two generators, I said it was going to be an and, so we have this one and this one. And when you have that in multiplication, it's going to be first one times the second one, or basically that value squared. And so we just take that probability and square it, and we get 0.0022. All right, that's all I have for this week.